Hello, grade 12. Welcome back to the channel. In today's lesson, we're going to be looking at work, energy, and power. And we are checking that May-June 2017 paper, SCE, so Senior Certificate Examination. So let's go, right, for you guys, because you'll be writing your exams for June, so in May. Then let's go check it out. Then question 5. It says the diagram below shows a boy skateboarding on a ramp which is inclined at 20 degrees to the horizontal. A constant frictional force of 50 Newton acts on the skateboard as it moves from P to Q. Consider the boy and the skateboard as a single unit of mass 60 kg. So we must consider them as 60 kg, the boy and the skateboard. Now they say ignore the effects of air friction. 5.1 says draw a labeled free body diagram showing all the forces acting on the boy skateboard unit while moving down the ramp from P to Q. So we can see that P to Q is that inclined surface there. So we must draw a label free body diagram, and then the first thing we want to check there is how many marks we are given. So this indicates the forces will be having there. So 3 marks for 3 forces. Let's go. So 5.1, we understand here that the boy on the ramp will experience the gravitational force, which is always there. So we can just start by faintly drawing that. Remember, you must then erase that incline. It's just to help us draw our free body diagram. Then we have our normal force now perpendicular to the surface, so it will be slanting like that. And then having to draw our FG parallel, so I like the one that is resolved. I always vouch for the one that is resolved because it also helps you in terms of calculations. So we have FG parallel and moving up there. So remember, the ramp has friction, so we have the kinetic friction there. And then down here we have the FG perpendicular, right? So now for this they'll be marking 1 mark because remember, FG perpendicular and FG parallel, these are components of weight. So you have the second force, that's normal force perpendicular to the surface, and we have the kinetic frictional force, which is obviously opposing the direction of motion, right? Then if you draw the one that is not resolved, you're obviously going to have something like this. This is your normal force, and then down like that, that's your FG, gravitational force, and then acting up the slope like that will be your kinetic frictional force. So this is how you'll have your free body diagrams. So the one that is resolved would look like this, and the one that is unresolved will look like that. So both these free body diagrams are correct. Now we have point P and Q on the ramp are 25 meters apart. The skateboarder passes point P at a speed of VI and passes point Q at a speed of 15 meters per second. Right, so we are given the speed at Q, which is 15 meters per second, but then we are not given the speed at P. We are only given an unknown value, VI. Now 5.2 says state the work energy theorem in weights. The work energy theorem in weights, let's quickly run to that. We have work energy theorem states that the net work done on an object is equal to the change in the object's kinetic energy. So if you're in an exam and then you kind of forgotten that, you just look at the formula sheet and then you'd find that you have something like this, right? So this tells you that the definition. So the work energy theorem states that the net work done, W net, is the net work. So the net work done on an object is equal to the object's change in kinetic energy. So as you can see here, the W net, the net work, is equal to the change in kinetic energy, right? So that's an easy way to remember that definition. Now 5.3 says use energy principles to calculate the speed VI of the skateboarder at point P. So now once you see this energy principles, you know that you have to run quickly to your formula sheet, right? So we want to use energy principles and we are not limited as to which one we should use. They just say use energy principles. So if they put it like that, if they put your question like that, then you have the option of using the work done by non-conservative forces if there are any frictional forces. In this case, we do have the frictional force, so we can use the WNC, and we can also use the W net, right? So you can use that one, you can use this one, but then there's the other one in energy principle, which is the one of conservation of mechanical energy. So ME, sum of ME is equals to sum of mechanical energy at A and mechanical energy at B. Now you cannot use this one because, as you can see, we have frictional forces. This only applies when we have no friction. So this one is completely an isolated system. This works in an isolated system where we are saying there will be no loss of energy. So this one wouldn't work. But then what we would use is the work done by non-conservative forces, which will be putting our frictional forces, or this one. But then if a hint I'm going to give you now, if the question above says state the work energy theorem, then below it asks you to calculate the same fashion that we have here. In 5.2 it says state the work energy theorem, and then in 5.3 they're saying use energy principles. Then the way to go about it is just to use the work energy theorem. It is the safest formula, and then considering the fact that they asked you to state that work energy theorem, it means it is best to use it, right? Then for our formula, W net is equals to change in EK, and then having this, we will have W net as work done by FG parallel plus the work done by FK, right? Remember our free body diagram was like this, right? So remember I told you that I always vouch for the one whereby you resolve, because you can see all the forces there. So we had the normal force here, and then we had the FG perpendicular there. So if you can check here, we have our horizontal forces. Our horizontal forces is FG parallel and FK, right? So this one is going in the direction of motion positive, and this one is going in the negative direction of motion, right? Opposite direction of motion. Remember, with work energy and power, if we have a force going in the direction of motion, we indicate its angle as 0 degrees, and if we have a force that is acting against the direction of motion, we indicate the theta as 180 degrees. So now let's come here. Remember, work is equals to the force times its displacement and the angle between the force and the displacement, right? So which is the theta there. Now the F is the force that we are dealing with, the force of interest, right? So in this case we are having FG parallel, and we know FG parallel can be written as mg sine theta, and then now we put our displacement delta x, then we have cos theta. Then what is the work done by FK? The work done by FK is FK delta x cos theta. Now let's break down the change in K. We can write it as half m Vf squared minus Vi squared. Okay, now we can start substituting. They say the combined mass of the boy and the skateboard is 60 kg. So let's have our 60 multiplied by 9.8, and then sine, what is the angle? 20 degrees. Then our delta x, we've been given to be 25 from the statement. As we can see here, the displacement from P to Q is 25 meters. Now we have our cos theta here. The theta here is the one for the direction of the force and the angle between the force and the displacement, which here we're going to have 0 degrees, since we are saying the displacement and the FG parallel are going in the same direction, so there will be no angle in between them, right? So this is 0 degrees. Note the difference between this theta here and this theta there, right? The theta in here is for the incline because we are working with FG parallel, and the theta here is the one, the angle between the force and the displacement. Then what is our FK? We've been told in the statement that they said it's 50. There's a frictional force of 50. And then delta X again is 25. Then what is the angle between the frictional force and the displacement? That's now 180 degrees. So we say cos 180 degrees, right? Then here we have half. The mass is 60, and then the VF, remember the velocity at Q is 15, so we have 15 square minus the VI, which we are looking for, we are not given, right? Now if you punch all this in your calculator, you have something like 3,777.69 6107. So you don't want to round off as yet, because remember it might affect your answer. You only want to round off in your final answer to at least 2 decimal places. Then if we have this, we can just take this 30 to this side, to the left hand side. So we have 30 VI squared, and then we take all this to the other side, so 6,750 minus all that. We want to have 2,972.303893. Then at this point we can just divide by 30, divide both sides by 30. Then our VI squared is equals to 99.0767. Then we can square both sides. Let's square both sides. Then our VI gives us 9.95 meters per second. And that's how you have it. Now let's look at question 5.4. It says calculate the average power dissipated by the skateboarder to overcome friction between P and Q. Now if we look at our free body diagram, which is obviously having that FG parallel and the FK this side, we do understand that in order to overcome friction, we have to have our FG parallel being equal to the FK, right? So to overcome friction, calculate the average power dissipated by the skateboarder to overcome friction, right? So in order to overcome friction, the skateboarder will have to exert the same force, which will be equal to this 50 newtons. So it will have to exert a force that is equal to the frictional force. Now at this point, we can see that choosing our formula, we have 2 formulas for power, which is this one to calculate P average and also that one. We do understand that we'll be using this one only if we are given change in time, right? But then here they wanted the power average, and then we can see that we can calculate the V average since we know the velocity at P and we know the velocity at Q. Remember, to calculate the V average, we need to say VI plus VF over 2, right? Then the force here would be that 50 newton, which is the force that will have to be exerted by the boy in order to overcome that friction of 50 newtons. So we have P average is equal to F times V average. What is the force that the boy needs to exert? That's 50 newtons. Then the V average will be the velocity at P plus the velocity at Q over 2. Now let's substitute that. We have 50. Then what is the velocity at P? This is the one that we just calculated, 9.95. Then what is the velocity at Q? We are given it's 15, and then divide that by 2, right? So if we multiply all that, we have 623.75. And remember, the SI unit for power is watts.